Okay, let's look at the Solow growth model. So this is a model of economic growth that was developed by Nobel laureate Robert Solow. The model describes how long-run economic growth is affected by nation saving, population growth, and technological change. The setup of the model. First, let's consider the supply side. We're going to use a production function, and it's going to assume constant returns to scale, which means a doubling of all inputs will exactly double the economy's output. For convenience, we'll express all quantities on a per worker basis. So I'm going to take this production function up here, and I'm going to divide everything through by L. And we get this result right here. So the left-hand side is just output per worker. We're going to use lowercase letters to represent quantities per worker. So we're going to let lowercase y equal output per worker, which is just output divided by the number of workers. Lowercase k will be the capital labor ratio, or capital per worker, which is the capital stock divided by the number of workers. And the function here is just going to be a function of lowercase k now. So output per worker is a function of capital per worker. So let's derive a per worker production function. Here we have this Cobb-Douglas production function, constant returns to scale, the exponents sum to 1. So we're going to derive the per worker production function. Doing that, we'll get this. L to the 1/2 divided by L leaves us just with L to the 1/2 in the denominator. And so using our lowercase letters again for per worker quantities, we have our per worker production function. Let's do another example. So if you have this production function, we can turn that into a per worker production function by dividing everything through by L. So L to the 0.75 divided by L leaves us with just L to 0.25 in the denominator. And that'll simplify very nicely to this. All right, moving on. Let's talk about the demand side. We'll put this on a per worker basis. So output comes from consumption and investment. We're ignoring the government in this model, so there's no G. And so the consumption function we could write as the following, where this 1 minus this S here is the marginal propensity to consume, the fraction of income spent on goods. S is the fraction of income saved, the saving rate. And we can plug this consumption function into the demand here. So where we have C, we're going to replace it with this result right here. And just simplifying the right-hand side, 1 times y and minus S times y. And simplifying further, these y's will cancel, and you'll be left with S times y equals I. Or we could say investment equals S times Y. The amount of saving per worker equals investment per worker. And remember that the production function is just a function of capital. So we can substitute this f of k in for y, and you have another expression for the investment function. Let's add depreciation to the model. D is the depreciation rate of capital. It's the fraction of the capital stock that wears out each year. The amount of capital that depreciates each year is going to be D times K, depreciation rate times the capital stock. And we can talk about the change in the capital stock. It's going to be the investment minus depreciation. How much we add to the capital stock, how much is wearing out of the capital stock. And just in shorthand notation, that'll be represented as follows. So the change in capital stock. And if we want, we can remember that, as we saw on the last screen, that the investment function is S times this function here. So making a substitution in for I, you'll sometimes see this expression for the change in capital stock written this way. So the change in capital stock equals investment minus depreciation of the existing capital stock. Let's talk about the steady state, the long-run equilibrium of the economy. The capital per worker is going to be constant. It's not going to increase. It's not going to decrease. The output per worker is going to be a constant. And consumption per worker will also be constant. So when we reach the steady state, these things will never increase or decrease. They'll stay constant. So the steady state level of capital per worker is K star, and it occurs when the change in capital equals 0. So with the per worker quantities constant, the total output, total consumption, total capital will increase at the rate of population growth. I'm not going to show that in this video. So for example, output increases with the rate of population growth, but output per worker is unchanged. So a key feature of the steady state long-run equilibrium is that things on a per worker basis stay constant. So approaching the steady state, some things to keep in mind: capital is going to be subject to diminishing returns. So increases in capital per worker increase output per worker, but at a diminishing rate. And the amount of depreciation increases at a linear rate with increases in capital per worker. So a couple scenarios. If investment is greater than depreciation, the capital stock grows and output increases the following year. So eventually capital and output will rise until the economy reaches a steady state where capital per worker is unchanged. And another possibility is investment will be less than depreciation, and the capital stock shrinks and output decreases in the following year. Eventually, capital and output will fall until the economy reaches a steady state where capital per worker is unchanged. Let's take a look at these ideas numerically. So we're going to look at the example of transitioning to a steady state. In this case, investment will exceed depreciation. So let's start with this production function, again on a per worker basis, and let's k equal 4. So if k equals 4, as we have in the table, we're going to see that y equals 1.59. So a few other things here: the savings rate, depreciation rate. So in year 1, again, if k equals 4, output per worker is 1.59. That means investment per worker, saving times output, 0.4 times 1.59, again the saving rate up here is 0.4, means investment will be 0.64. So that's where this 0.64 is coming from. The consumption is just going to be y minus I, or 1.59 minus the 0.64, or 0.95. So that's consumption per worker. In terms of depreciation, our capital stock is at 4, but the depreciation rate is 0.1. So our capital stock will decrease by the amount of depreciation, or 0.4. So that's the 0.4 now. And so the change in capital is investment minus depreciation, or 0.24. So we're going to be adding to the capital stock. So the capital stock will be slightly higher in the following year, or in year 2. So in year 2, capital will be 4 plus the 0.24, or 4.24. With 4.24 units of capital per worker, output per worker is 1.62. When output, or you could say income as well, when output or income is 1.62, investment is going to be 0.648. So that's where I is coming from. And that means consumption now will be 0.972. The total amount of depreciation is going to be 0.1 times our capital stock, or 0.424. And our change in capital will be positive, not quite as large as the last period, but still increasing. And this process will continue until the capital stock and output will reach its steady state when capital per worker, or the capital labor ratio, is 8. So let's show that in the next slide. So in year N, let's say the capital labor ratio is 8. This means output per worker is 2. Investment per worker is 0.8. Consumption per worker is 1.2. The depreciation is 0.8. So our change in capital will be 0. And so in year n plus 1, nothing will change. So we're at this steady state now where the capital labor ratio stays constant, output per worker stays constant, consumption per worker stays constant. So all the per worker quantities are going to remain constant once we reach this steady state. All right, let's move on. Let's look at the other example of transitioning to the steady state when investment is less than depreciation. Here, the change in capital will be negative, output per worker will fall, the capital labor ratio will fall, and so on till we reach our steady state where K equals 8. So plugging 27 in to our per worker production function, assuming the same values for the saving rate and depreciation rate, in year 1, we'll have the following. And so you'll see our change in capital will be negative. The investment that has been undertaken is smaller than the total amount of depreciation, so the change in capital will fall. So in year 2, we're going to start with a lower capital labor ratio. Going to get less investment, less consumption. But once again, the change in capital will still be negative, not quite as negative as the earlier year, but still be negative. And year 3, we'll start with less capital, lower output, and so on. And this process will continue until the capital stock and output will continue to fall until we reach the steady state capital labor ratio of 8. And we can look at this graphically. So the steady state level of capital per worker is 8. So that's where the investment and depreciation per worker are the same. If K is less than 8, investment will be greater than depreciation, and the capital stock and output will rise until, once again, K equals 8. And then we just saw in our last example, if we started with K equals 27, for example, investment will be less than depreciation, and as a result, the change in capital will be negative until we reach a capital stock of K equals 8. Okay, that's it. I'll stop here.